Thank you everyone for being here. And we are back to Student Talks with the presenter this time being Etaash Katiyar, who will be talking about category theoretic products. So this is a nice talk on category theory. And if you have any questions during the talk, you can always put them into the chat, which you can access by pressing the chat box on the toolbar. If you're watching this talk on YouTube, don't forget to like, comment, subscribe, heart react, everything. And
You can also ask questions on the comments. I might end up answering them. Hello, everyone. Thanks for coming to my talk. And as you already know, I'll be talking about category theory, and specifically these things called products in category theory. Why? Because I think this is like one of the simplest examples of category theory being like a unifying many different types of maths. And this is all maths that 1A undergrads have seen, which is what makes it especially good. Yeah, in the middle of my talk, I'll have pauses for questions. Okay, so this is the structure of my talk. I'll start with describing the field as a whole. Then I'll go into the details of what categories are. Then I'll get into the definition of products and have a lot of examples. And then duality, and I'll touch on some of like a really cute example that I found. What is category theory? Section 1. I'll start by this quote by Freeman Dyson. Some mathematicians are birds, others are frogs. Birds fly high in the air and survey broad vistas of mathematics out to the far horizon. They delight in concepts that unify our thinking and bring together diverse problems from different parts of the landscape. Frogs, on the other hand, live in the jungle below and see the flowers that grow nearby. They delight in the details of particular objects and they solve problems one at a time. This is really good framing for seeing like what category theory tries to do, and category theory tries to give us a very bird's eye view of maths, extremely zoomed out and trying to find things that are common in extremely disparate branches. There's also other reasons to be interested in it, and it's been useful for studying other areas of maths, as in like how groups eventually help you talk about topologies, like using algebraic topology. Category theory like gives you specific machinery which has turned out to be useful for algebraic geometry and other areas. So, I mean, you might just end up learning it because you're interested in other maths. For those of you who care about foundations, it provides an alternative to set theory. Like, you know how you can write everything, or almost everything in maths in terms of sets and like build everything up from just the empty set and a few axioms for sets? Instead, you can do everything using categories, and it ends up being, I think, a much more natural way to think about things. And lastly, but not least, it's also useful for studying programming languages. So theoretical computer sciences have found use for it. And if you want to see more about this, look at the programming language Haskell. And what was surprising to me is how young of a field it is. It's only about 80 years old compared to the rest of the pure maths you do. Like, it barely reaches into the previous century. Yeah, these are a few of the founders of category theory. Not founders, but people who've popularized it and used it for really cool stuff. Now, I'll start my next section. What is category theory? What are categories? First, start off with the definition. So the category C consists of a collection of objects, which you denote obj of C. And for every two objects, we have a collection called HOM of A and B. And they're often denoted as the collection of maps between A and B. And these satisfy these following axioms, which are for every three objects and two maps, a map F from A to B and a map G from B to C, there exists like this composite map. So you can compose the maps, and the domains and codomains of the maps have to make sense. Yeah, the note about this, the composition is associative in this sense. And there exists an identity map for every object. And this the properties of that are just these identity laws. And then there's this last bookkeeping rule, which means that the domain and codomain of every map is unique. And that's a very abstract definition, but like, here's the prototypical example you should keep in mind when every time you think of this is if you let your objects be the collection of all sets, and HOM S, T is all the functions from S to T. Yeah, your maps are just functions between sets, and your objects are just the collection of all the sets. And it's easy to see that these satisfy the axioms. As in, yeah, we're very familiar with function composition, and we know it's associative. For every set, we have an identity map. And if you compose the identity map with any other function, it leaves the other function unchanged. And maps have well-defined domains and codomains. This is a simpler category. This is one way you can visualize categories is as a bunch of objects and a bunch of arrows. The arrows here represent maps, as in G is a map from B to C. So G is in hom B, comma C. And this is the composite map. And this is how we denote the identity maps going from an object to itself. Yeah, another definition is that of a commutative diagram. These are really useful tools for like pictorially visualizing when two maps are equal. So a commutative diagram is just, if we say this diagram commutes, what we mean is no matter how we follow the arrows and compose maps along the way, we get the same result. So going from A to D to C gives us the same thing as going from A to B to C. It's the same thing as going from A to C. And this diagram commutes if and only if we have these equalities. Just to visualize this, then we have, these are the commutative diagrams for, this represents the identity laws, and this represents the associativeness. That if you do F and then you do 1B, like the identity on B, it just gives you F. And if you do the identity on A and then you do F after that, you just get F again. And the associative things are similar. And yeah, I'm gonna have a lot of examples and like maybe retread the same ground, but I guess I just prefer to cover more depth and less breadth. So you might get tired if you prefer a lot more content. In a category, we have a bunch of objects and a bunch of maps. And yeah, the prototypical example to keep in mind is that of the category of sets. And essentially, we have maps and we can compose the maps. And here's like other examples of categories. The collection of groups is the objects, and hom G, comma H is all the group homomorphisms from G to H. Now, groups are like sets, but with this additional structure on top of them, which like explains how the group elements interact with each other. And yeah, so what we do here is we want to study groups. So we make the objects all the groups, and then all the maps or the arrows in our category are just like the type of maps that we care about. Like pretty much all the maps between groups that we care about are group homomorphisms. We can do the similar thing with topological spaces, like pretty much lots of fields of maths, and so all topological spaces and then continuous functions between topological spaces forms a category. You can fix a field you want to work over and then think of the vector spaces over that field. And the homomorphisms, you can probably guess by now, just the linear functions. And here's a more formal example. We have any set S with a binary reflexive transitive relation. The objects are just the elements of the set, and the maps are this thing. It should be, yeah. There's an arrow between S and T if and only if S is related to T under this relation. And composition is defined as this, as in go from S to T to R. And this corresponds to this map. And this element corresponds to this map. And we have composition like that. If I didn't mix up my letters, but I think you get the picture. Yeah, this is much better visualized for the example. And this is the natural numbers with division. Yeah, we need reflexive so that we have identities, and we need transitivity so that this last thing we composed makes sense. So the natural numbers with division form a category of this type. So 2 divides 2 is represented by this, and 2 divides 4. And you don't have a map between 4 and 18 because 4 doesn't divide 18. And yeah, again, summarizing, categories are just objects and maps between the objects, and there's sensible ways of composing those maps. And the prototypical example to think of is sets, but then you can also apply your definitions on groups, topological spaces, vector spaces. You can also like smooth manifolds and smooth maps as well, if you want to. And also you can make like lots of formal examples as well, like a set with a transitive reflexive relation. You can also make categories out of other categories. Like people work with the category of all categories, where objects are just all the possible categories, but I'm not going to get into that. And yeah, I think this is the time to pause for questions, but yeah, I mean, I'm willing to answer like more general questions as well. Like they don't have to be just clarifying things. Okay, then seems like there aren't any so far. Now, the definition of products. Just get onto the definition then. For any two elements of a category, this triple A cross B, and then these two maps. This triple is a product if A cross B is an object, and PA is a map from A cross B to A, and PB is a map from A cross B to B. And yeah, this thing at the bottom here, that's the triple. This is the key property of a product. For every object Z, there exists a unique map F A cross B from Z to A cross B, like this map. And this is unique, such that this diagram commutes. So that just means that if you compose PA of FA cross B is FA, and same with B. And yeah, this feels very abstract at first, and I'll cover a lot of examples to like show you why this works.
Sorry, there was just a question in chat which pretty clarifying. Is home AB obviously a single element?
It doesn't have to be a single element, like in general. Yeah, it doesn't have to be a single element in general, but it's a single element in that last example. In this example, it's a single element. Hopefully that answers your question.
Yeah, thanks. And then Sean's asking what FA and FB are, I think, in the diagram right now.
Oh, okay. Yeah, I guess so. For every object Z and two maps, FA that goes to A and FB that goes to B. Oops, that was a typo. Yeah, it should be for all objects Z and and a pair of maps FA and FB.
So are PA and PB essentially projections? Is that?
Yes, they're
okay.
They're called projection maps. Yeah, that's the next thing I was going to talk about. PA and PB are the projection maps, and we think of the product as this whole thing. It's when we ask for a product, we get this thing, not just this object, because the product doesn't make sense if you don't have a way of getting back to your original elements as well, like in a sense. Yeah, from this definition, like it's not too hard to show that but I won't show it, but it's not too hard to show that you can get uniqueness up to isomorphism, as in if any two different like triples satisfy this definition, then both of their objects are isomorphic. And what does isomorphism in a category mean? F from A to B is an isomorphism if like it has a left inverse and a right inverse. So this boils down to being a bijection in the category of sets, or a group isomorphism in the category of groups, because like isomorphism of vector spaces, which is a bijective linear map, and the homeomorphism of topological spaces. It's like what is generally like the canonical isomorphism of every subfield of maths. Yeah, now I think I'll try to discuss some intuition of this, and before like delving into examples. We can think of maps as carrying structure from one object to another. And what I mean is like think about it in terms of groups. Like if we have a group homomorphism from G to H, then the first isomorphism theorem tells us that G mod kernel of F is isomorphic to some subgroup of H, and that subgroup is the image. You can think of G mod ker of F as, in essence, like some of the structure of G. And I mean, it could be all of the structure of G if the kernel is trivial, but like if it's not, it's some of the hidden structure inside, and we're forgetting what the kernel says. But what the homomorphism tells us is that this structure also lives inside H. So this homomorphism is telling us that there is some structure in G which also lives inside H. And keep that in mind, you might be tempted to agree with my next explanation of this, why this definition makes sense. So for every object Z, some of the structure inside Z is being sent into A, and some of it is being sent into B through these two maps. And the product A cross B is the optimal structure to encode all of the structure sent in through these two maps. And the encoding is just this map, like the new unique map that we did get. A cross B doesn't have too little structure because we can recover the original maps just by applying P of A to our encoding. And we don't have too much structure because of the uniqueness. I guess that's a bit harder to justify, but it's more like, if it wasn't unique, then you could somehow argue that there's extra space inside of A cross B. And yeah, it turns out that if you actually concretely apply this definition, it does become in a sense, the minimal amount of structure you need to encode all possible structure going into A and B. Yeah, just showing the diagram again to refresh your minds. And now I'll delve into the example of sets. Fortunately enough, in the category of sets, this product is isomorphic to the Cartesian product of sets, which is the ordered set of ordered pairs. And I'll eventually show a proof outline of this, but for now, to just understand why this works is considering, instead of an arbitrary set Z, let's just consider the singleton set Z containing just one element, namely the element 1. And yeah, the definition becomes for every pair of functions fa from the singleton to A and fb from the singleton to B, there's a unique fa cross B from the singleton to A cross B. And you get the projection map properties. But any function f from the singleton to another set is just a choice of element of S. As in, this is literally just specifying an element of the codomain. So if I just rephrase the previous definition, instead of function from singleton to A, but in terms of this new language, L choice of element, we get for every pair of elements of A and B, there's a unique element of A cross B. And from this element, we can recover our original two elements through projection maps. And you see how the uniqueness makes this there's no extra elements, and the projection maps that you can encode all of the elements. And this works for sets because sets are determined by their points, but I mean, yeah, you can just prove that you can eventually prove that it works for all sets Z and not just singletons. And for the proof, I don't really care about the proof as much. It's not really that insightful in a way. Many of the proofs in category theory aren't exactly insightful, but they're more they just show you that the definitions you chose were the right ones, hopefully. Or they show you that they were the wrong ones. Yeah, so we just need to show that the Cartesian product and your the projection maps that you're familiar with satisfy this definition of a product. And then there's a straightforward way you can prove that if any two objects in any category satisfy the definition of a product, then they're isomorphic. So up to isomorphism, you get that it's this. And I mean, here's a proof. Maybe I'll share the slides later if people really want to see the proof. But yeah, I think it's more fun in the talk itself to delve into more examples. And it's just groups, we get the direct product of two groups, which you would have hoped for. In vector spaces over reals, we get the direct sum of vector spaces. And if you just thinking of Rn as an Rm, then it's just putting the two vectors on top of each other, as in if this was length n and this is length m. In the category of topological spaces, we get the product topology, which is also reassuring. Yeah, these are all different things, defined very differently in all the different courses. What surprised me about this is that when we form a category, we just take all the objects we care about, and then we look at all the maps between things that we care about, and then we forget the internal structure. As in, the category of groups has no idea how any two elements of a certain group are going to compose and what's going to happen to them. But you still get like the sensible direct product of two groups. And same thing with like topological spaces. Like it is, and yeah, that's what I found really cool about. And it's surprising that category theory actually managed to do things like this. And this happens again and again. And this is the most surprising example, is that we have naturals with division. Remember what I defined earlier when I made the naturals into a category with division. And the definition tells us that, okay, for any two natural numbers a and b, we have projection maps from the product to A and from the product to B. So the existence of the projection map tells us that A cross B divides A and A cross B divides B. Yeah, for all elements in naturals, Z divides A, and so that Z divides A corresponds to FA and Z divides B corresponds to FB. This implies that Z divides A cross B because we have the existence part from the definition, and we don't need uniqueness because HOM only contains at most one element in this category. But we immediately recognize this as the definition for the greatest common divisor. And yeah, and if you like want to phrase it in terms of the intuition I provided earlier, it's like, if you think of like the divisibility structure of the naturals, and what matters are the factors of different numbers. And so the greatest common divisor is the optimal object which encodes the divisibility properties of A and B. And yeah, this is a time for break for questions, if there are any.
Sorry, could you just explain again what you mean by this is a definition of the GCD? Which exactly part of this is a GCD?
The product. This number is the greatest common divisor of A and B.
Right. Okay. Because, yeah. That makes sense. Yeah. Okay. Sorry. Thanks.
Oh yeah, I guess I should have said that. Yeah. And this is the last thing I'll talk about, the concept of duality. I'm talking about duality because there's this really cool example that I got from the Philosophy of Math lectures by Tom Foster in the Maths department. That's at the end, and I'm building up to it, so you'll have to wait. So what is duality? It's an important part of category theory, which gives you extra definitions and fun things for free. And like very, very vaguely, it's just like reversing all of the arrows in all of your diagrams and in your categories. And yeah, and the new object is often just called the previous object, but with a co-prefix to it. So what I'll show you is like the co-product. And this is the definition of a coproduct, and you'll see it's very similar to that of a product. And a coproduct of two objects, A, comma B, is this triple, the coproduct object itself, and then these two maps, called the inclusion maps. The coproduct object is an object, and these maps go from, like, it's reversed now. It's from A into the coproduct. And the property it has is for all objects Z and maps now from the other direction, FA from A to Z and FB from B to Z, there's a unique function F sub coproduct of A and B from the coproduct to Z, such that this diagram commutes, which just means that if you like consider like the inclusion of A in the coproduct and then you do your map, then you get your original map that you cared about back. And this kind of gives you the opposite notion, as in for every object Z and structure going into Z, A coproduct B captures all of the structure that you can put into Z from A and B. This is like literally just same diagram as the previous one, but reversed. And what does the coproduct look like in different categories? In the natural numbers with division, it's reassuringly the least common multiple of two numbers, because you just replace the word is divided, A divides B, and you replace that with A is a multiple of B everywhere that the relation occurs, essentially. And in the category of vector spaces, the coproduct and the product apparently give the same thing. And the direct sum of vector spaces and the direct product, if you bother to define it, are actually the same thing. And in the category of sets, we get the disjoint union. Actually, yeah, I talk about topological spaces as well. I haven't put it in the slides. It's that you get a topological space which like imagine you have this disk and another disk, and the co-product of these two spaces is just like the two disks put together and they don't interact in any way like this. Just like putting two different objects together in a way that they interact the least amount possible. And as a topological space, it's just like take the union of them, and then you take like union of open sets in these two things. If I haven't messed that up, yeah. And in the category of sets, it becomes a disjoint union. And the disjoint union is just like, it's just like the regular union of two sets, but you postulate that the sets that you're taking the union of are disjoint. And you can just like formally set it up as this, as in you have the pair a comma 0 for elements of a and b comma 1 for elements of b, and that's just roughly make sure that a and b are disjoint. And we don't really care about the 0 and 1. They're just, yeah. So this is the example that I was building to. And let's imagine we're working in the category of finite sets, and all your objects are just finite sets, and the maps are just functions between finite sets. So it's just the regular category of sets, and you remove everything that's not finite. Now, isomorphism in this category just boils down to bijection. So if you try to think like isomorphism is an equivalence relation, and if you think of the isomorphism classes again in this, you just get all sets of size 0, all sets of size 1, all sets of size 2, and so on. So you just get like an isomorphism class for every natural number. And yeah, you can like, I'm just going to call these 0, 1, 2 from now. Like this is identify these by their number. And this last result is just that the operations of product and coproduct respect this equivalence relation in the sense that if A is isomorphic to A dash and B is isomorphic to B dash, then A cross B is isomorphic to A dash cross B dash. And the same with this. So this lets us define the product on these sets themselves. And what we get is just addition and multiplication on the natural numbers, as in the equivalence class of 3 plus the equivalence class of 2 all times the equivalence class of 5 will give us 25, right? Yeah, 25. And that, yeah, I found that really surprising. And yeah, I guess this highlights how you could serve as an alternate foundation for maths. But this is like weak evidence for that, because I mean, in some sense, construction was a bit arbitrary, but then like, this isn't something that I expected at all to get from it, that like the product of numbers is actually kind of like in this like very abstract sense, the same as the product of sets. Yeah, and that's all. Thank you for coming. The background is just a random category theory diagrams that I found in Wikipedia, and hopefully you enjoyed.
Okay, thanks. That was really cool. Are there any questions? Anyone? If that's a question in the chat. Yeah, so do you get anything if you let products and co-products interact?
Yes, it depends on the category you're working in, because like in some categories, like the product distributes over the co-product, but in others you get like other like complicated structures. But yeah, I don't know enough about it. I just know that there's certain categories where it distributes, and I think they're called linear categories, but I'm not sure. Yeah. But yeah, people have studied like which categories and like the nice properties you can get out of the ones where they interact nicely. But I don't think there's like a very general, like in general, they don't interact that well.
So then does that mean that depending on how well they interact, you get essentially models for different kind of sets? So for example, if they interact well, you get something similar to fields, and then if they interact worse, you get something which is worse, like so for example, something which wouldn't be commutative, or that kind of stuff.
I think
Can you build this kind?
commutativity is like built into the thing. Like you get commutativity for just from the definition.
Okay.
So yeah, this
Yeah.
last
Yeah.
example here was a really like fringe example. It's not really like the objective intense study. It's not really like, I don't think it's like particularly like central. I think I don't know. I don't think you'd find many other examples of this sort of stuff happening, but like the rest of it, like having a definition which works for one category and then seeing it works for many others is like is what to expect. Category theory.
Yeah.
Yeah.
Okay. And here's another question: whether can this be used to prove that multiplication of the naturals is distributive?
You can use this to prove that it's associative, but I think you can prove distributivity, but I know you can prove associativity of multiplication and the naturals.
And then from this example, from this last example, how can you be sure that they behave the same way as the naturals do? So when you say that this is a module of the naturals, because if you want to prove from this that the naturals are associative or distributive or whatever, you need to know that they behave the same way, right?
I mean, yeah, every time we introduce like a new definition for something, right? Like we have to make sure that the new definition, like as a more meta-mathematical, like a more historical point, like when Peano probably came up with his axioms, you won't just like say that these are the natural numbers and then agree that these are the natural numbers. Instead,
Yeah.
you'll see that like these behave as much as we can tell as the previous like idea naturals we had, and like we can prove in our old framework that this new definition is equivalent. So instead of taking this old definition, let's
Yeah.
just use the new definition and then work backwards. So like I guess quote advocating unquote that like you can take this as a definition and then just like first show that it makes sense with your previous work and then take this and then work backward from there if you wanted to.
Yeah. Okay. Yeah, this makes sense. Okay. Thank you. Yeah. Yeah. Thanks a lot for the talk. It was really interesting. And yeah. So thanks to everyone for coming.